Hey everyone, and welcome. So today we're diving into the incredible and sometimes kind of scary world of the industrial Internet of Things. We're talking about connecting giant factories, power grids, all that physical stuff to the cloud. And let me tell you, it's a real high wire act, full of amazing potential, but also some serious dangers. Okay, let's get into it.
And really, this is the question at the heart of it all, right? What actually happens when you take this sensitive, proprietary data from, say, a huge automotive plant and expose it to the internet? You're trying to get all those valuable analytics, but you're also potentially opening a door you really don't want to. All right, so let's tackle the first big hurdle, security. How in the world do you build an impenetrable digital fortress around your most critical systems while still letting that valuable data get out to the cloud where you can use it?
So picture this. You want to get all this juicy real-time data, temperature, pressure, you name it, from the factory floor up to a cloud platform like AWS so you can analyze it. The problem? Any normal two-way connection is a two-way street, and that means it's a potential attack vector. Any path for data to get in is a massive risk.
So how do you solve this? Well, with a really elegant piece of engineering called a unidirectional security gateway, or USG. The core of this thing is what's called a data diode. And just like the slide says, it's a one-way street for your data. But, and this is the most important part, it's enforced by the physical hardware. It's not just software. This literally makes it physically impossible for an attacker to send anything back into your secure network. Data can leave, but absolutely nothing can get back in, period.
And this diagram right here, it lays it all out perfectly. See over on the left? That's your secure industrial network, the factory floor. Now follow the arrows. The data flows through that unidirectional security gateway in the middle, our digital air gap. It sends the data across that physical one-way diode, and then, as you see on the right, it safely publishes it to the AWS cloud. Because of that physical barrier, no virus, no hacker, no threat of any kind can ever make the return journey from the internet back into that factory. And look, the numbers don't lie. In real-world tests, this setup just nails it. A perfect 100% across the board on everything that matters, keeping data pure, keeping it private, and controlling who sees it. You just can't get more secure than that. It's basically Fort Knox for your data. Okay, so our data is secure, locked down tight. But what happens when you're dealing with not just one device, but thousands of them? This brings us to our next monster of a challenge, conquering massive scale. Let's take a real-world example, a company called LumiGrow. Imagine these enormous modern greenhouses. They are packed with thousands of smart grow lights. The environment is huge, it's humid, it's full of metal structures. It's a complete nightmare for wireless signals like Wi-Fi. So how do you reliably talk to every single one of those lights? Well, the first plan was the obvious one, just slap Wi-Fi on everything. But yeah, as you can see here, that fell apart fast. The more lights they added, the more congested the network got, until it was just completely unreliable. It just couldn't scale. They needed a much smarter way to do things. And this is where the clever part comes in. Instead of having every single light try to call home to the cloud, they set up this brilliant leader/follower system. The cloud only talks to a handful of leader devices using Wi-Fi. Then, each leader acts like a squad commander, broadcasting the orders to its local group of follower lights using super efficient, low-energy Bluetooth. It's a simple, elegant way to let the whole system scale up massively without ever clogging up the main network. Okay, so our system is secure. It's scalable, awesome. But there's one more killer hurdle. What do you do when everything works, but it's just too slow? Welcome to the battle for performance. This was the harsh reality for a team building a high-performance network traffic analyzer. They built their system, but it just hit a brick wall. It choked. It couldn't handle traffic any faster than 25 megabits per second. I mean, in the modern world, that's just not going to cut it. The aggregator was a total bottleneck. And to get past this, they really had to take this quote from Node.js creator Ryan Dahl to heart. This wasn't a problem you could solve by just throwing more powerful hardware at it. No, they had to go deep to really fundamentally understand what their code was doing under the hood. So they started profiling their app on a free BSD system, and boom, they found the smoking gun. The application was eating up a staggering 35% of the CPU just to run. That is an insane amount of overhead and a massive performance killer. But after some serious, deep-level engineering, check this out.
They got that CPU usage all the way down to around 10%. That is a game-changing improvement. It's what allowed them to go from choking at 25 megs to handling a full gigabit per second. So how'd they pull it off? So here's the kicker. The magic wasn't a faster chip, it was smarter code. Two big things. First, they used something called memory pooling. Think of it like a restaurant having a big stack of cleaned plates ready to go, instead of having to wash a single plate every single time a customer orders. It's way more efficient than constantly asking the operating system for memory. Second, they optimized their locking mechanisms, which basically reduced the digital traffic jams, where different parts of the code were just sitting around waiting for each other. This was pure hardcore system optimization.
All right, so we've been through the trenches here with security, scale, and performance. After seeing these real-world battles, what are the big takeaways? What are the key principles we can use to build our own successful IoT systems?
First off, you've got to plan for scale right from the beginning, just like the LumaGrow team did with that leader/follower model. Don't let it be an afterthought. Second, isolate your critical systems. That data diode is the perfect example of putting security first in your design. Third, you have to benchmark and profile. You can't fix a bottleneck you can't see, so measure everything. Fourth, pick the right tool for the job. For IoT, that often means lightweight protocols like MQTT, which are built for low-power devices on shaky networks. And finally, build for resilience. Assume things will go wrong and have a backup plan, like automatically switching from Wi-Fi to cellular, so you never, ever lose critical data. So when you see engineers knocking down these huge challenges, security, scale, speed, one by one, it just blows the doors wide open for what's possible. It really makes you wonder, and this is the exciting part, with these problems getting solved, what part of our world is going to get a whole lot smarter next?